Example 6. This is a 2015 AP exam question, and it says, consider the differential equation dy by dx is equal to 2x minus y. Now, one thing to notice about this differential equation is that it is not separable because it's 2x minus y. It needs to be a multiplying factor to be able to separate the dy with the y's and dx with the dx with the x's. So part A of this question asks, on the axes provided, sketch a slope field for the differential equation on the points indicated. So to do the slope field then, what we're going to do is we're going to take the coordinates and plug them into the differential equation. So we'll start with the top left. So x is 0, y is 2. When x is 0, y is 2, we get a slope of negative 2. So I'm going to draw in a negative 2 slope segment there. So I'll do that in a different color so it stands out a little bit more. So we can have a negative 2 slope segment through there. We plug in x is 0, y is 1. Okay, we end up with a slope of negative 1. So we get a 45-degree slope section. And at x is 0, y is negative 1, we get a slope of positive 1. So we're going to have a 45-degree slope section through there. Okay, then we go to x is 0, x is 1, y is 2. X is 1, y is 2, we get the slope is 0, so we get a horizontal line segment there. X is 1, y is 1, so we get a slope of positive 1. And lastly, x is 1, y is negative 1, we get a slope of positive 3. So we're going to have a relatively steep slope section through there. Okay, so those are my slope sections. Part B says find d squared y over dx squared in terms of x and y and determine the concavity for all solution curves of the equation in quadrant 2 and give reasons for your answer. Okay, first thing we're going to do is find the derivative. So we're going to differentiate dy by dx, and when we do this, I get d squared y over dx all squared. Differentiating that expression, we get 2 minus 1, and then because we are differentiating y, we're going to go y prime. Okay, so one thing that that difficulty with this is that now we have a second derivative in terms of y prime and not y. But what we can do is we can use original definition here. This expression is y prime, and we're going to replace it. Replace that y prime with that expression. So when we do that, we get d2y over dx all squared. It's going to be equal to 2 minus, and instead of y prime, I'm going to replace that with 2x minus y. And so that represents my second derivative. So simplifying that, I'm going to end up with the second derivative is equal to 2 minus 2x plus y. Okay, so we now have the second derivative. The second part of this says determine the concavity. Okay, so determine the concavity in quadrant 2. Okay, quadrant 2 is in here. In quadrant 2, we have a negative x and we have a positive y in this quadrant. Okay, so this being quadrant 2. If I plug in negative x and positive y into that quadrant, I just need to have sign analysis to determine if the concavity is positive or negative, or the second derivative is positive or negative. So if I write this out, I know that I have a negative x, positive y, so I end up with 2 minus 2 times a negative value plus a positive value. When I look at the signs of this, I know that regardless of the values of x and y, I know we're going to end up with positive, and that means the second derivative is positive, which indicates a positive concavity. So I know that the concavity in quadrant 2 is positive. Okay, so we can then, our reason is that our second derivative is equal to positive, therefore we have positive concavity. For part C, it says, let f of x be the particular solution to a differential equation with initial condition f of 2 equals 3. Does f have a local min, max, or neither at x equals 2? Well, for something to have a local min or max, the first derivative must be equal to 0. So we know that f prime is equal to 0, or in this case, y prime, or dy by dx is equal to 0. So we know that what we want to do is find y prime when x is 2, y is 3. Well, we can substitute into our original dy by dx equation, and we end up with 2 times x is 2 minus y is 3. Okay, just highlighting that. This 2 and 3 are what we're plugging into the equation. When we do that, we end up with 4 minus 3, which is equal to 1. Well, y prime at 2 and 3 is not equal to 0, so it can neither have a local min or max. So neither local min or max.